Hi guys, so today we'll be solving LeetCode problem, closest rooms. So there's a hotel with n rooms. The rooms are represented by 2D integer arrays. Rooms where rooms at I position is room ID size denotes that there's a room with room number, room ID and size equal to size I. Each room ID is guaranteed to be unique. So we are also given k queries in a 2D array queries where queries as j index. The answer to j query is the room number ID of a room such that the room has a size of at least mean size, and the absolute difference between ID and prefers is minimized. If there's a type in the absolute difference, then use the room with the smaller ID. Okay, so if there's no such room, then the answer is -1. So it can be a little bit complicated, but I will guide you guys through this example. So as you guys can see, there is 3 rooms. Room number 2 has size of 2, room number 1 with size of 2, and room number 3 with size of 2. So 3 rooms has size of 2. They have the same size, right? So we have 3 queries. The first query is that has a prefer of 3 and the mean size of 1. So both of 3 of these rooms actually satisfy the first part of the question, right? Of a question, which is that it has to have the size of at least mean size, right? 3 rooms have size of 2, so they both can be a candidate. But the closest will be this guy, since 3 minus 3 is 0. So the answer is 3. And we are going to do that for each query, right? So how can we do it in a smart way to actually negate all of the redundant work? What do I mean by redundant work? If we do it by brute force way, for each query, then we will go through all of the room in the hotel, right? And then we will take a look at which validated room has the minimum absolute difference, and then we're just going to append it to the result array. But that's going to be O(n) square, and it's going to not be efficient enough. Now there's actually a way that we can use sorting to go from the queries with the largest mean size, right? And then when we go from a query with the larger mean size to a query with a smaller mean size, we are going to append additional rooms into our queue, right? And then now for each queries, we will have a queue to store all of the room ID, right? And then now our task is to find the lower bound, the one that is exactly smaller or equal than preferred, and the one that is exactly larger than preferred, right? After that, we are going to compare these two guys, and then we should see which one should yield the minimum absolute difference, right? The minimum absolute difference has to come from the guys that is just below it or just above it, right? Okay, so that is the solution. We are going to sort our queries from largest mean size to smallest in mean size. We are going to sort our rooms from largest size to smallest size, and we are going to append additional rooms into our queues when we come from a queries to the next query, right? And then how are we going, what data structure are we going to use for our queue? We need to use sorted list. In Python, we can import it from a library called sort containers. What does it do? Basically, if we use heapqueue, right? If we use heapqueue module, then the order of all the elements in the heap is not going to be sorted. But if we use sorted list, it is sorted, that's one part, but it is also indexed. Therefore, we can use binary search to perform finding the lower bound and the upper bound, right? Okay, so let's implement it. Queries is prefer mean size index for index, prefer mean size enumerate queries. Why do we need index? Because we are going to sort our queries, and then if we need the index to find the position that we are going to insert into our result array, right? Sort and that x minus 1 rooms sort lambda x. Okay, after that okay, so if there are still room that hasn't been pushed into our queue, we are going to do this, right? If len rooms is actually larger than 0, and then rooms 0, what is the mean size that's at index 1, right? Here is actually larger or equal to, it's not q, but rather prefer mean size index, right? It's actually larger than mean size. We're going to add it into our sorted list. We're going to pop the first guys out. The first side will have room ID as first position, and then side as the second position, right? Of 0, then we're going to append it into our queue. Okay. So now is the binary search part. Okay, so let's say that if so let's create our result variable. I'm going to initiate it to -1. Why? Because if a query is not relevant, then we need to return -1. So might as well just going to prefill it with all -1. So if length of queue is actually equal to 0, it's actually larger than 0, mean we have candidate in our queue, right? We are going to do binary search. So just I'm going to call it just below is going to be equal to bisect refer queue below. Then as above, bisect refer queue, and then above. Okay, so now I'm going to compare them. If apps of just below minus refer smaller or equal to apps of as above refer we're going to append the guy that's smaller, right? Else we're going to append the guy as above. Not append, but rather index, right? Because we need to maintain the order of the queries. And that's it. Okay. Now let's construct our binary search function. Okay. Type is equal to below. X equal to 0. Then Q -1. Y L smaller than R. Okay. Basically the same, but here we need to do larger, and then we go to set our R to mid. Here we're going to set our L to mid +1, and I hope that's enough. And then yeah. We need to add it, right? That I don't know. Okay. L it's going to u in time limit exists, because here we need to. Okay, I think that's it. Okay, so the time complexity is actually going to be O n log n space complexity is going to be O of n, right? Okay, so we do a little bit of sorting here and there, and then we're going through our array of query size of n, and then for each of them we're going to do a binary search on room size of m. That's actually O n log m, right? Okay, so the space complexity, we need to maintain a cube size of m. That's actually O of m. Okay, so that's it for today. I hope that it makes sense to you guys, and see you guys in next video.